Hi, in this video I'm going to talk about history of sampling theorem. Now, in the literature, the sampling theorem is known as Shannon sampling theorem, but sometimes it's also known as the Nyquist-Shannon sampling theorem. So, who is Nyquist and what is his role in sampling theory? We are going to try to answer these questions. So let us do this comparatively. So H. Nyquist, in fact Harry Nyquist, lived in between 1889 and 1976. Okay. Now we are going to see his role in sampling theory. Now, on the other hand, we have Claude Shannon, and he lived between 1916 and 2001. Okay, so Shannon was much younger than Nyquist. Now, Nyquist obtained his BS and MS degrees in EE from North Dakota University. So his BS and MS are from North Dakota University, and these are degrees in EE, electrical engineering. Shannon obtained his BS degree in electrical engineering and in mathematics from University of Michigan. And he obtained both degrees in EE and in math. Okay, the PhD of Nyquist is from Yale University, and the PhD degree is in physics. The MS degree of Shannon is from MIT in EE. And the PhD of Shannon is also in Massachusetts Institute of Technology in math. Okay. Now, both worked in Bell laboratories, but Shannon also worked in MIT, in Massachusetts Institute of Technology, as a professor. So, Nyquist worked at Bell Labs, and also Shannon worked at Bell Labs, but also in MIT as a professor in EE. Okay. Now, as I have told you at the beginning of this video, the sampling theorem is known as Shannon sampling theorem, but sometimes in the literature it is known as Nyquist-Shannon sampling theorem. So the contribution of Nyquist to sampling theory is in fact present in his 1928 paper on telegraphy. So, Nyquist's paper on telegraphy this paper appeared in 1928, and there, in fact, in that paper, Nyquist discussed certain technical points related to the transmission of signals in a telegraph system. And the so-called contribution to later sampling theory is in fact related to the sampling rate. Okay, so the Nyquist rate, okay, in this paper, the concept of later, of course, this name is given later, the concept of Nyquist rate is introduced. Okay. Now, what is Nyquist rate? In order to understand what we mean by Nyquist rate, we have to remember the sampling theorem. Remember, if we have a band-limited signal with a maximum frequency omega m, okay, the sampling frequency omega s must be greater than 2 omega m, okay? So we here remember that a band-limited signal can be reconstructed without aliasing if the sampling frequency omega s is greater than 2 omega m. Okay, the frequency 2 omega m is known as Nyquist rate in the literature. Okay, so 2 omega m is known as Nyquist rate. But in certain textbooks, this is also called Nyquist frequency, so one has to be careful. The correct term is 2 omega m is known as Nyquist rate. Nyquist frequency, on the other hand, is when you perform sampling, you use the frequency omega s. Omega s divided by 2 is called Nyquist frequency. So, omega s divided by 2 is known as Nyquist frequency. So the role of Nyquist appears to be the following. In his paper, of course, his discussions were completely related to telegraphy, and he didn't consider the representation, the problem of representation of band-limited signals and etc. But he introduced the concept of Nyquist rate. Okay? So this is the contribution of Nyquist. On the other hand, The interpolation formula. Now, what are the contributions of Shannon? The Shannon, later of course it is called the Shannon interpolation formula. Which is x of t equal to, for a band limited signal with the highest frequency, omega m, and when it is sampled by omega s greater than 2 omega m, therefore we have no aliasing. In that case, x of t can be reconstructed from its samples as follows, and from minus infinity to plus infinity, x of m ts sinc t minus m ts divided by ts. Remember, this sinc function is coming from the low-pass filtering action in frequency domain. And this formula is the formula introduced by Shannon. So the Shannon interpolation formula is introduced in a paper by Shannon in 1949. Sometimes it is 1948 or 1949 because the paper was published in January of 1949, so the work appears to be in fact done in 1948. So the paper by Shannon was about the theory of communication in the presence of noise. So if we look at that paper, we see the Shannon interpolation formula for the first time in that paper. So let us see this now. Okay, now this is the paper of Shannon where we see the Shannon interpolation formula for the first time. So the name of the paper is Communication in the Presence of Noise. Now if we look at where it is published, it is published in the Proceedings of the IRE in 1949, January 14, 1949. But this is a reprint in 1998 as a classic paper. So this is a very important paper. Okay, we have seen the name, Communication in the Presence of Noise. In fact, he is trying to establish a theory of communication in the presence of noise. Now, in the second page, we see the sampling theorem, given as Theorem 1. Now, let us read the theorem and see how the terminology is different from the modern terminology we use at the moment. If a function f of t contains no frequencies higher than w cycles per second, CPS, it is completely determined by giving its ordinates at a series of points spaced 1 over 2 w seconds apart. Okay? And if we follow his reasoning, we see the Shannon interpolation formula in equation 7. You can see that the samples of the signal are here as xn, and here we have the sinc function appearing as the multiplier. So this is an interpolation formula in terms of the samples and shifted versions of the sinc function, and it is a representation of the band-limited signals. He mentions this as the first statement of the theorem. The function f of t contains no frequencies higher than w CPS. Okay, so the theorem known as Shannon Sampling theorem is sometimes known as Nyquist-Shannon Sampling theorem, but the contribution of Nyquist is only in terms of the inequality omega s greater than 2 omega m, and 2 omega m is known as Nyquist rate. Okay? He, in fact, has no contribution to the representation of a band-limited signal in terms of a reconstruction from its samples. Okay? That is completely a contribution of Shannon. So thanks for watching.